Hey everyone, and welcome back to the channel. Today, we're diving deep into the fascinating world of physics, exploring 10 mind-bending concepts that might surprise you. Buckle up, because we're about to explore the strange, the theoretical, and the downright mind-blowing. Imagine the universe as a giant cosmic dance party. All the elementary particles, like electrons and quarks, are the dancers. But some seem to have more weight or inertia, making them move a bit slower on the dance floor. These are the massive particles. Others are lighter and zip around with more ease. But what gives these particles mass? That's where the Higgs boson comes in. The Higgs boson is linked to a field that permeates all of the space, called the Higgs field. Think of this field like a giant invisible mosh pit at the cosmic dance party. The more a particle interacts with the Higgs field, the more it gets bogged down, like wading through thick mud. This resistance is what we perceive as mass. Particles that don't interact much with the Higgs field can move more freely, hence their lighter mass. For a long time, the Higgs field and boson were just theories. But in 2012, scientists at the Large Hadron Collider, a massive particle accelerator, achieved a breakthrough. They were able to smash protons together at incredibly high energies, recreating conditions similar to the Big Bang. This collision produced particles consistent with the Higgs boson, providing strong evidence for its existence. The discovery of the Higgs boson was a major milestone in physics. It helped us understand how particles acquire mass, a fundamental property in our universe. Without the Higgs field and boson, the universe we know wouldn't exist. We wouldn't have stars, planets, or even life itself. There's still much to learn about the Higgs boson. Scientists are actively researching its properties and how it interacts with other particles. This ongoing investigation could shed light on unanswered questions about the universe's origin and the nature of mass itself. Again, we will use our imagination to make it easier to make sense of the world of dark matter and dark energy. Imagine a giant cosmic pie. When we look at the universe, the visible matter, stars, planets, galaxies, makes up only a tiny slice, about 5%. The rest is a cosmic mystery pie filling, consisting of two major ingredients, dark matter and dark energy. Dark matter, estimated to make up about 27% of the universe, is invisible to our telescopes. We can't directly see it, but we know it's there based on its gravitational influence. Here's the evidence. Galaxy rotation. Galaxies spin too fast to be held together by the gravity of the visible matter alone. Something invisible, like dark matter, must be providing the extra gravitational pull. Gravitational lensing. Massive objects like dark matter can bend light due to gravity, acting like a cosmic lens. By observing how light from distant galaxies warps, scientists can map the distribution of dark matter. The nature of dark matter remains a great unknown. Scientists have proposed various candidates, such as weakly interacting massive particles or axions, but none have been definitively detected yet. The search for dark matter is an ongoing effort, with experiments using sophisticated detectors deep underground or in space. Dark energy, the other major component, estimated at 68% of the universe, is even more mysterious. Unlike dark matter, it doesn't seem to interact with gravity in the usual way. Here's what we know. Accelerating expansion. Observations of distant galaxies show the universe is expanding at an accelerating rate. This suggests a force, like dark energy, is pushing everything apart. We have very little understanding of the nature of dark energy. Some theories propose it's a property of space itself, or perhaps a leftover energy from the Big Bang. Understanding dark matter and dark energy is crucial to unlocking the secrets of our universe. Their vast presence shapes the universe's evolution and expansion. Scientists are constantly developing new theories and experiments to unravel these mysteries and create a more complete picture of the cosmos. Before we get into this question, I would like to warn you right away that there will be a lot of theories. Therefore, if you are not a theorist, just skip this part, timeline in the description. And yes, we will still use our imagination. So, imagine a river. Water flows steadily downstream, never back upstream. That's how time feels in our everyday experience. It flows in one direction, from the past to the future. We can remember the past, but predicting the future perfectly is impossible. This one-way flow of time is known as the arrow of time. But why does time seem to have a direction? Here are some key ideas from physics. Entropy. The second law of thermodynamics states that in an isolated system, entropy, disorder, tends to increase over time. Think of a freshly shuffled deck of cards. Over time, it naturally becomes more disorganized. This tendency towards increasing disorder might be what creates the arrow of time. The past is a more ordered state, while the future is a more probable state of increased disorder. The Big Bang. Our universe had a definite starting point, the Big Bang. This moment marks a clear beginning in time's progression. Everything that has happened since the Big Bang has unfolded in a specific sequence, contributing to the feeling of a past, present, and future. The expansion of the universe. The universe isn't static, it's constantly expanding. This expansion might be a fundamental property of the universe that contributes to the directionality of time. While these concepts help paint a picture, the arrow of time isn't without its mysteries. What were the laws of physics like in the very beginning? Did time flow in the same way? Some theories suggest a period of inflation after the Big Bang where time might have behaved differently. The intense gravity within black holes might distort time in ways we don't fully understand. Is time travel or a reversal of time's arrow possible under such extreme conditions? These are fascinating questions in theoretical physics, but there are currently no confirmed observations. Exploring the arrow of time is crucial because it's linked to the fundamental laws of our universe. It helps us understand the origin and evolution of the cosmos, the relationship between cause and effect, the nature of reality itself. Superfluidity isn't about a special type of liquid, it's a special state of matter. Usually, liquids experience some level of internal friction or viscosity as their molecules interact and resist flow. However, when certain materials like helium are cooled to near absolute zero, minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit, their atomic motional energy plummets. This allows them to enter a new state where the atoms act more like a single, unified wave function, essentially super-cooperating. What are the properties of superfluidity? Frictionless flow. Once in motion, a superfluid will continue flowing indefinitely without any loss of energy due to friction. Imagine swirling a superfluid in a closed container. It would keep swirling forever. The fountain effect. Due to its perfect flow, a superfluid can defy gravity. If you place a narrow tube in a container of superfluid, the liquid can actually climb the tube and flow out continuously. Quantized vortices. While the bulk of a superfluid is frictionless, if you stir it, you can create rotating regions called vortices. These vortices come in quantized sizes, meaning they can only rotate at specific speeds. Superfluidity is still an active research area, but it has some potential applications. Ultra-sensitive instruments. Superfluids might be used in delicate scientific instruments where even the slightest friction could disrupt measurements. Frictionless bearings. Imagine frictionless bearings in machinery. Superfluid technology could lead to significant energy savings. Quantum computing. Some theorize that superfluid properties might be used in future quantum computers for faster and more efficient processing. Superfluidity is a fascinating phenomenon that challenges our classical understanding of liquids. Scientists are still unraveling the full extent of its properties and potential applications. Before we get to Fact 5, it's a good time to check if you are subscribed to the channel and have put a like. This will ensure that you don't miss the next video. In the classical world of everyday objects, observing something doesn't usually change its properties. But in the quantum realm, where particles behave very differently, the act of observing can actually influence their behavior. This is the observer effect. At the atomic and subatomic level, particles don't exist in a definite state like position or momentum all the time. They exist in a probabilistic state called a superposition, meaning they have a certain probability of being in multiple states simultaneously. The observer effect comes in when we try to measure a quantum particle's property, like its position. The act of measurement collapses the particle's wave function, forcing it to choose a definite state. Imagine a coin spinning in the air. It's both heads and tails until it lands. The act of observing it makes it land on one side. Similarly, measuring a particle's position fixes it in a specific location, but in doing so, we lose information about its momentum, how fast and in what direction it's moving, and vice versa. A famous demonstration of the observer effect is the double-slit experiment. Here, light, which can behave like a particle or a wave, is fired through two thin slits towards a screen. When we don't detect the light particles, photons, individually, they create an interference pattern on the screen, indicating wave behavior. However, if we place a detector to observe the passage of individual photons, the interference pattern disappears and light behaves like a stream of particles. The act of observing collapses the wave function and alters the outcome. The observer effect has significant implications in quantum mechanics. Uncertainty principle. The observer effect forms the basis of the Heisenberg uncertainty principle, which states that it's impossible to know both the position and momentum of a particle with perfect precision. The more precisely we measure one, the less we can know about the other. The nature of reality. The observer effect raises questions about the nature of reality. Do particles exist in definite states even when not observed? Or is reality somehow dependent on observation? The observer effect is a well-established phenomenon, but scientists are still exploring its deeper implications and potential applications. Understanding this effect is crucial for interpreting experiments in quantum mechanics and developing technologies like quantum computers. Imagine two coins linked in an extraordinary way. When you flip one, the other instantly flips the opposite side, no matter how far apart they are. That's the essence of entanglement in the quantum world. Entanglement is where two or more quantum particles become linked in a special way. Their fates are intertwined, so that measuring the state of one particle instantly tells you the state of the other, regardless of the distance separating them. This spooky-sounding phenomenon, famously described by Einstein as spooky action at a distance, has been experimentally verified and is a cornerstone of quantum mechanics. How does entanglement work? Here's a simplified picture. In the quantum realm, particles don't exist in definite states like heads or tails for a coin. They exist in a superposition, meaning they can be a combination of both states simultaneously. When two particles become entangled, their wave functions become linked. They act as a single entity, even when separated by vast distances. Measuring the state, like spin, of one entangled particle instantly collapses the wave function of both particles, forcing them to take on definite states that are correlated. Here's some examples of entanglement. Entangled photons, they are particles of light, can be entangled in their polarization, orientation of their electric field. Measuring the polarization of one entangled photon instantly tells you the polarization of the other, even if they're sent on journeys to opposite ends of the universe. Entangled electrons. Electrons can also be entangled in their spin, intrinsic angular momentum. Measuring the spin of one entangled electron tells you the spin of the other, regardless of the distance. Entanglement has profound implications for physics and technology. Challenge to locality. It challenges the idea that information can't travel faster than light. While no information is actually being transmitted faster than light, the correlation between entangled particles seems instantaneous. Quantum technologies. Entanglement is crucial for developing technologies like quantum communication and quantum computing. By harnessing entangled particles, we could achieve secure communication and solve problems impossible for classical computers. While entanglement has been proven, scientists are still unraveling its full potential and its deeper meaning in the grand scheme of quantum mechanics. It's not exactly a law of physics, but rather a philosophical thought experiment that explores the relationship between the universe's fundamental constants and the existence of life. The Anthropic Principle proposes that the laws of physics and the constants of nature, like the strength of gravity or the mass of the electron, are fine-tuned for the existence of complex life as we know it. If these values were just slightly different, the universe might not be capable of supporting life at all. Weak Anthropic Principle. This simply states that the universe we observe must be compatible with the existence of life because we are here to observe it. In other words, if the universe were fundamentally hostile to life, we wouldn't be around to contemplate it. Strong Anthropic Principle. This version goes further, suggesting that the universe's properties are not just compatible with life, but actively biased towards it. The laws of physics and constants might be fine-tuned in some way to favor the emergence of complexity and life. The Anthropic Principle has its fair share of criticisms. Confirmation bias. We can only observe the universe we exist in, so it naturally seems fine-tuned for us. However, there might be an infinite number of universes with different settings, and we simply happen to be in one that allows for life. Lack of predictive power. The Anthropic Principle doesn't predict anything new about the universe or the existence of life elsewhere. It simply points out the curious coincidence of the universe's properties and our existence. Despite these criticisms, the Anthropic Principle is a thought-provoking concept that encourages us to consider the immense scale and complexity of the universe, the delicate balance of forces that allows for life to exist, the possibility of other universes with different laws of physics. Think of the universe as a giant electrical party. Regular matter, like the protons and electrons that make up atoms, all have specific electrical charges. But what if there were a universe where everything had the opposite charge? That's the basic idea behind antimatter. Antimatter is composed of antiparticles, mirror images of normal particles with the same mass but opposite electrical charge and other properties like spin. For example, the antiparticle of an electron is a positively charged positron, and the antiparticle of a proton is a negatively charged antiproton. Antimatter is incredibly rare in our universe. The Big Bang is believed to have produced equal amounts of matter and antimatter, but these particles annihilate each other on contact, releasing bursts of energy in the form of gamma rays. This annihilation process means most antimatter was destroyed shortly after the Big Bang, leaving behind the universe dominated by matter that we see today. Scientists can create small quantities of antiparticles in particle accelerators. These high-energy machines collide particles at incredibly high speeds, creating conditions that can produce antimatter particles like positrons or antiprotons. Studying antimatter helps us understand the universe's fundamental laws and the processes that govern the Big Bang. Here are some potential applications. Positron emission tomography scans. In medicine, positrons are used in PET scans to image organs and diagnose certain diseases. Test of fundamental symmetries. Studying the behavior of antimatter can help us test fundamental symmetries in the laws of physics. Future propulsion? This one's speculative. Some theoretical ideas explore the possibility of using antimatter for future space travel due to the immense energy released during annihilation. However, large-scale production and storage of antimatter remain significant challenges. Imagine a gas of atoms all zipping around independently. Now, crank the temperature down to near absolute zero, minus 273.15 degrees Celsius or minus 459.67 degrees Fahrenheit. That's cold, isn't it? For certain particles called bosons, this extreme chill can lead to a bizarre phenomenon, the formation of a Bose-Einstein Condensate. Becks form because bosons, unlike their fermion cousins electrons, for example, don't mind sharing the same quantum state. In simpler terms, at these ultra-low temperatures, a large number of bosons can pile into the lowest available energy level, like a bunch of friends squeezing onto the same couch. This collective behavior is what defines a BEC, a macroscopic number of atoms acting like a single quantum entity. Becks exhibit some unusual properties. Superfluidity. Fluids normally have some internal friction, but Becks can flow without any friction whatsoever. Imagine swirling a BEC in a container. It would keep swirling forever. Extreme order. Becks are incredibly ordered systems, with all the atoms in a single quantum state. This is in stark contrast to the typical random motion of atoms in a gas. And don't forget about wave-particle duality. Becks showcase the wave-particle duality of quantum mechanics. The entire condensate can behave like a giant wave, exhibiting properties usually associated with light or other waves. Creating Becks requires sophisticated techniques to achieve the necessary ultra-low temperatures. Scientists use lasers or magnetic fields to trap and cool down clouds of atoms. By studying Becks, we can gain insights into the behavior of quantum systems at very low temperatures, the foundations of quantum mechanics, potential applications in areas like precision measurement and atom interferometry. We have said many times that black holes are regions of space-time with such strong gravity that not even light can escape. Anything that crosses the event horizon, the point of no return, seems to be trapped forever. But according to Stephen Hawking's theory, black holes are not completely silent. Hawking radiation stems from the bizarre world of quantum mechanics, which operates at the subatomic level. Here's the gist. Near the event horizon, the incredibly strong gravity can create fleeting pairs of virtual particles, like a particle and its antiparticle, from the vacuum itself. Sometimes, due to a quirk of quantum mechanics, one particle of the pair, let's say the antiparticle, might fall into the black hole while the other escapes. The escaping particle carries away energy, and this energy is borrowed from the black hole's immense gravity. Over time, this energy loss causes the black hole to slowly shrink and emit a faint glow of radiation, Hawking radiation. Hawking radiation is a theoretical prediction based on the combination of general relativity, gravity, and quantum mechanics. Here are some key points to consider. Extremely faint glow. The amount of radiation emitted by Hawking radiation is incredibly small, making it very difficult to detect directly. Black hole evaporation. The rate of radiation increases as the black hole shrinks, meaning smaller black holes would evaporate faster. However, even the smallest stellar mass black holes would take an enormous amount of time to dissipate completely. Information paradox. Hawking radiation raises questions about the information paradox. Black holes are thought to destroy information that falls into them, but Hawking radiation seems to lack any information about what fell in. This paradox is a topic of ongoing research. While not directly observed yet, scientists are actively searching for evidence of Hawking radiation. They are looking for ways to detect the faint glow or its effects on surrounding objects near black holes. That's all for today. Physics might seem abstract, but it's all around us. From the way your phone works to the incredible feats of engineering that allow us to explore space, physics plays a crucial role in our everyday lives. Don't forget to like this video if you enjoyed it, and hit that notification bell to stay updated on future content. See you next time.